Large language models generate text probabilistically. They predict the next most likely token based on training data, operating without any underlying epistemological grounding. For organizations deploying AI in high-stakes environments, this unconstrained generation acts as a significant liability. The model is guessing, not reasoning. In enterprise compliance, guessing carries severe penalties. A probabilistic output cannot be audited, verified, or trusted by a compliance officer. When an automated system flags a financial risk or rejects a legal document, regulators do not accept the algorithm's intuition as an answer. They demand to know the exact logical why behind the decision. Black box models fail this regulatory test by default. Their outputs cannot be traced back to a structured, repeatable methodology. The solution to this regulatory gap is method-declared AI prompting. Standard conversational prompting relies on open-ended requests and unpredictable outputs. Method-declared prompting imposes rigid architectural constraints on the model before it processes a single word of input. Instead of predicting the most likely response, method-declared prompting forces the large language model to adhere to formally verified schemas. By executing these strict analytical procedures, the model leaves a hard, transparent paper trail for every claim it produces. Surviving the current landscape of AI regulation requires shifting from probabilistic guessing to deterministic proof. This is an executive export matrix, the final output of a method-declared system. Here, a risk score of 5 triggers an immediate rejection. This rigid table structure decouples from typical conversational AI outputs. It delivers data in a format designed for decision makers, not chat interfaces. At the bottom of this export is the traceability block. This serves as the anchor for mapping every executive decision back to its logical origin. To understand how this compliance output is generated, we have to reverse engineer the highly technical prompt architecture operating beneath it. This 3D wireframe represents the declarative frame schema, or DFS. This is the underlying architecture that governs method-declared prompts. The foundational constraint is L1, ontological commitments. L1 forces the model to adopt a specific, explicitly declared worldview, establishing what the framework takes for granted before any analysis begins. This actively prevents the language model from drifting into its default perspective. The baseline assumptions are strictly controlled and documented. The next layer is L2, analytical objects. This acts as the targeting mechanism of the prompt. L2 instructs the model on which exact phenomena to extract from the source artifact. It dictates precisely what the model must observe and evaluate, ensuring it focuses only on relevant data points. This targeted extraction operates differently from standard RAG deployments, which often rely on unstructured, noisy text parsing. Without the L1 and L2 layers, the language model is simply summarizing a document without a governing methodology. Without L1 and L2 in place, the output lacks a stable interpretive ground. It becomes a summary that cannot be verified against a consistent logic. As this diagram shows, the top layer of the stack is L3, linguistic operations. This is the active processing layer. L3 dictates the precise analytical moves and logic procedures the model must execute on the targeted data. Attached to this stack are the calibration dials, D1 for scale, D2 for observer, and D3 for temporality. These dials calibrate the output dimensions. By establishing the zoom level and observer position, results from different frameworks can be composed together without causing logical contradictions. Together, the complete L1 through L3 stack transforms the large language model from a text generator into a precisely calibrated analytical engine. Building the architecture is only the first step. Next is the quality control phase required for a prompt to enter the active enterprise library. Every prompt artifact must undergo formal verification. This document is the taxonomy review schema. It is a strict 10-point checklist used to audit the prompt. Passing this checklist formally promotes a prompt from a draft state to a deployable, stable state. This gatekeeping ensures that the ontological commitments, analytical objects, and linguistic operations are mathematically and logically isolated prior to deployment. Once verified, we move to the operational execution phase. Artifacts are not blindly fed into a schema. This flow diagram illustrates the triage node, which serves as the mandatory first step for any incoming, unclassified artifact. The triage node evaluates the raw artifact to classify its framework-neutral structural properties. Based on that classification, the triage node formally routes the artifact to the correct verified schema within the library. Formal verification paired with strict triage routing eliminates ad hoc, untraceable model behavior. We can now return to the executive export table shown at the beginning of this process. This schematic draws a hard boundary to enforce separation of concerns. The core analytical pipeline sits on the left, entirely separated from the executive export layer on the right. Data flows one way. The export layer is forbidden from altering the underlying analysis logic. When the export maps a risk score of 5 onto the output, it does so directly from an L3 operation, for instance, an authentication failure identifying a fabricated source. Isolating the analysis engine from the formatting output ensures the final risk score remains objectively untampered. This diagram traces a glowing path from an action item through the traceability block, anchoring directly into the specific L3 node that generated it. This proves the system's compliance to regulators. Any output produced without this direct reference block is mathematically invalid. This mechanism establishes a perfect auditable paper trail, spanning from the raw input text to the final verdict. You can trace the exact logic map, in stark contrast to the indefensible black box of standard generative AI deployments. Method-declared prompting represents a structural shift in how we extract utility from large language models. This approach satisfies regulatory demands by radically constraining the operational boundaries of the model, rather than attempting to alter its internal neural weights. Standard black box deployments are increasingly incompatible with audit requirements. The glass box provides the traceability that regulators now expect.